My great pleasure and honor to introduce Dr. David Gross, the Chancellor's Chair Professor of Theoretical Physics and former Director of the Kavli Institute for Theoretical Physics at the University of California, Santa Barbara. He has been a central figure in particle physics and string theory. His discovery of asymptotic freedom, the primary feature of non-abelian gauge theories with his student Frank Wilczek, led Gross and Wilczek to the formulation of quantum chromodynamics, the theory of strong nuclear force. This completed the Standard Model, which details the three basic forces of particle physics: the electromagnetic force, the weak force, and the strong force. Dr. Gross was awarded the 2004 Nobel Peace Prize in Physics with Pulitzer and Wilczek for this discovery. He has also made seminal contributions to the theory of superstrings, a burgeoning enterprise that brings gravity into the quantum framework. His awards include many national and international prizes and medals. He holds honorary degrees from institutions in several countries and is a distinguished member of several prestigious National Academy of Science in various countries. We are fortunate to have Dr. Gross's graceful presence at this event and look forward to hear his thoughts and vision on the future of science and technology.
Your Majesties, Your Royal Highnesses, ladies and gentlemen. For more than 100 years, the Nobel Foundation has handed out these generous prizes and hosted these magnificent dinners. All of this was made possible by the generosity and the vision of Alfred Nobel. But can it continue? To continuing having such splendid parties, two things are required. First, an inexhaustible supply of money, but also, equally important, an inexhaustible supply of great scientific discovery. The first requirement seems to be guaranteed, since the Foundation spends only the interest and wisely invests the capital of Nobel's bequest. The second requirement might appear harder to satisfy. As knowledge increases, could the pace of scientific discovery slow as more and more problems are solved? Fortunately, nature is as generous with its problems as Nobel was with his fortune. The more we know, the more aware we are of what we know not. Indeed, the most important product of knowledge is ignorance. The questions we ask today are more profound and more interesting than those asked years ago when I was a student. Many of those we have answered. But back then, we did not possess enough knowledge to be intelligently ignorant and to ask the wonderful questions we ask today. Some wonder whether someday we will arrive at a theory of everything and run out of new problems to solve, much as the effort to explore the Earth ran out of new continents to explore. While this is conceivably possible, I am happy to report that there is no evidence that we are running out of our most important resource, ignorance. How lucky for science, how lucky for scientists, and how lucky for the Nobel Foundation. Thank you.
And how lucky for PanIIT Please join me in welcoming Dr. David Gross.
Thank you. Well, I could spend the next half an hour or 3 hours discussing some of those wonderful questions that remain to be answered and that we now pursue. But instead, I want to talk more about strategy. How do we go about addressing these questions, and of what good are the answers? So I'm going to talk about the importance of basic science, and in particular, theoretical sciences, and in particular, theory institutes. Now, everyone loves science, including our political leaders around the world who talk about the importance of science, of STEM, of research. The last Prime Minister of China said eloquently, "The history of modernization is in essence a history of scientific and technological progress." And from a Chinese point of view, I firmly believe that science is the ultimate revolution. Our own president, Barack Obama, said, "Science is more essential for our prosperity, our security, our health, our environment, and our quality in life than it has ever been." But what they're really referring to in these remarks is what I would call technology-driven science. The justification for investigating questions whose answers have ready applications to science is obvious. The question I would like to address here is why curiosity-driven science? Sometimes it's called basic science, sometimes it's called fundamental science, but its most important characteristic and definition is curiosity-driven science. There are 3 reasons. The first, and perhaps the most important, certainly to the scientists who pursue their careers in curiosity-driven science, is to satisfy our curiosity. After all, that is what we are as a species. Homo sapiens have evolved to understand and control the world around us. And the search for the understanding of the world around us and its origins, the origin of our species, of life, of the universe, are at the core of what it is to be human. They're at the core of our success as a species, and they're at the core of our greatest achievements. So the first answer is just that, to satisfy our curiosity. Now, of course, scientists have an important role, an important responsibility, not just to satisfy their own curiosity, but to feed the hunger of their friends and colleagues and fellow citizens of the world, to satisfy their curiosity, to transmit this knowledge that we gain of the world to others. The other reason for doing basic science, which does not have necessarily immediate applications, is to motivate excellence. Many of the most intelligent, inquisitive, and innovative people, young people especially, are attracted to basic science, to the big questions that are out there, and to the attempt to answer those questions. So when I travel around the world and lecture to young people at high schools or universities or graduate universities, I'm amazed at the level of excitement and curiosity and passion that these people show. And they are attracted to science because they are passionately, exercised by the large questions. What is life? How does it work? What is the origin of the universe? What is matter made of? Et cetera, et cetera. Often, in their later years, and I'm sure that was the case for most of you, later as they go into higher education and truly learn what science is, they discover that in addition to these big speculative questions that people like me are engaged in, there are many, many other fascinating areas of science all over the map, and applied science and technology, and they feed into those areas. But unless there is that original motivation to address the big questions, many of them will turn immediately to business school or law school. Basic research benefits all of society by educating and training thousands of students who will choose to enter the workforce not only in academic research, but as workers in many diverse industries. And I make this argument in support of basic science to politicians and leaders across the world because many of them don't realize that unless they have a strong presence and, in fact, a leadership role in the basic sciences, they will lose their talent to those countries and those centers of research that do. And finally, there is the point that basic science is the way truly novel technology is created. So here I like to quote another politician, not my favorite politician over the years, but she expressed beautifully this point, Maggie Thatcher. She said that although basic science can have colossal economic rewards, they are totally unpredictable. And therefore, the rewards cannot be judged by immediate results. The greatest economic benefits of scientific research have always resulted from advances in fundamental knowledge rather than the search for specific applications. For example, transistors were not discovered by the entertainment industry, but by people working on wave mechanics and solid-state physics. Nuclear energy was not discovered by oil companies with large budgets seeking alternative forms of energy, but by scientists like Einstein and Rutherford. So why is this true? This is true, that exploration in the basic sciences leads innumerable examples to great breakthroughs in areas which nobody could have predicted and applications which nobody could have imagined. And the reason, I think, is very simple. It is that nature is much smarter than we are at posing good questions for research. Nature is much smarter than the bureaucrats who dole out research funds. Nature is much smarter than the market. The best example of this, and I unfortunately don't have time to give you many examples, is quantum mechanics, which was discovered by theoretical physicists like me who are doing speculative research into the working of the atoms and structure of matter 100 years ago. And they came up in order to understand the atom with this crazy theory called quantum mechanics, which still mystifies many, but was essential to understanding how the atom works, how their molecules work, how ordinary matter works, to understand intimately the structure of atomic matter. And its applications dominate modern technology. All of our modern technology is based on our understanding that was gained through the development of quantum mechanics, atomic physics, molecular physics, nuclear physics, the transistor, the integrated circuit, the laser, all of modern technology. And this revolution, which was totally speculative theoretical work initially in the 1920s, has not yet been completed by far. Many of my colleagues and I believe that we still have a very limited idea as to the possible forms of ordinary matter. Some of ordinary matter is very ordinary and found around us on Earth. But now that we are able to understand and control atoms at the atomic level, so-called nanophysics, size of atoms, we can construct and understand novel forms of matter, and we have actually no idea how much more interesting and novel forms of matter might exist and might be constructible and surely will be used. So the best is yet to come. Now, I want to talk about ways of pursuing basic knowledge. And the examples that started the idea of institutes already came about at the same time quantum mechanics was developing. Niels Bohr, who invented the first model of an atom based on quantum theory, founded an institute in Copenhagen which had a very important role in the development of quantum mechanics. And a few years later, in order to deal with some of the scientific refugees from Europe, the Institute for Advanced Study was started in Princeton. These are famous and remain famous institutes whose idea was not just to have a university with a professor with his own lab, but to bring people together, to work together, and create something new. In 1960, after the war, Abdus Salam, who is the only Pakistani to win a Nobel Prize for his work on the electroweak nuclear force, founded the International Center for Theoretical Physics, which has played a seminal role in providing a place where people from developing countries can come and get started in physics. And now the ICTP also plays a fundamental role in helping develop physics and the physical sciences, the mathematical sciences, biological sciences around the world. Salam made a very important point when he founded this institute. He said it is impossible just to talk about technology transfer. If you want to help the developing countries, you can't just transfer technology to them. One must first talk about science, and technology transfer comes later. Because unless you are very good at science, you will never be good at technology. And he also said that it is insulting to tell developing countries that you shouldn't strive to be first-rate in science, but rather just borrow or use the technology that have been developed in the advanced countries. Science, after all, what happened to this one? Scientific thought is the common heritage of mankind. And it is incredibly discriminatory to exclude half the world or more from that common heritage. So he founded the ICTP to provide equal opportunities so that all can engage in the creation of physics and science for the benefit of all mankind. Now, as was said, I, until recently, was the director of the Kavli Institute for Theoretical Physics in Santa Barbara, which follows those examples as an institute that brings together scientists from all over the world. We run 12 scientific programs a year for 1 to 3 months, bringing 1,000 or so physicists, and we interpret physics to mean everything from cosmology and the history of the universe to string theory, to condensed matter physics, to biology, which I call the physics of living matter, together, to come together for 3 free months and work on problems at the frontiers of science. This has been an extraordinarily successful model for the last 36 years. Now, all the examples I gave you were institutes of theory, and there's a reason why theory is special for such activities and why it plays such an important role. Theorists, unlike their public image, are not loners. They're intellectual extroverts, although sometimes they're social introverts. They crave engagement with other theorists. They collaborate in joint projects with groups of 1 or 2 or more. They continually talk to each other and share ideas and compete and criticize, and that's how they work. They share these ideas very freely, exposing the ideas first to constructive criticism as constructive suggestions and criticism. It's an incredibly cooperative effort. And face-to-face interaction is irreplaceable. And that's why these theory institutes have played such an important role in advancing the theoretical sciences. Not just physics, theoretical physics, but mathematics, bioinformatics, biophysics, astrophysics. In fact, those very names and the division of science into different disciplines of physics, chemistry, biology, geology is totally artificial. It's a distinction that's created by university rectors and deans to pigeonhole scientists in different departments. If you go out and look at nature and the problems it poses, there's no label on the problem. This is physics, chemistry, biology. And indeed, today, some of the most exciting developments taking place are at the boundaries of this traditional fields and require the efforts of many different scientists. And theory serves as the glue for interdisciplinary efforts. This is partly because experimental science, and science is mostly experimental, requires labs devoted to answering a particular problem and big groups working on a particular problem, whereas theorists, luckily, can flit from problem to problem and use their analytic skills. And sometimes it's very useful to go into a new area with new problems because you can bring skills that have been useful in another area. Now, I gave you an example of 4 of the most famous of these institutes around the world: the Niels Bohr Institute, the Institute for Advanced Study, the International Center for Theoretical Physics, and the Kavli Institute for Theoretical Physics. But imitation is the sincerest form of flattery. And in the last decades, institutes of this type have sprung up everywhere, not just in physics and mathematics. MISRI at Berkeley next door, AIM. There are 5 other, or 6 other actually, institutes of mathematics throughout the United States, the Newton Institute in Cambridge, England, and in physics, the Institute for Nuclear Theory in Seattle, the Galileo Institute in Florence, the Perimeter Institute in Canada, and many others. The Max Planck Institute for Physics of Complex Systems, a copy of the Kavli Institute in Beijing, and the International Institute of Physics in Natal. But what about India? So, in my opinion, and I formed this opinion in a very strong way about 10 years ago when I visited India for a prolonged tour, India has enormous and largely untapped potential. And that is dramatically evident nowadays when India's economic growth is beginning to match that of China. And I found these two graphs really illuminating. The global economic forecast of the World Bank has India's growth per annum up there with China. The US is down here. And this projection, I forget who made, which is more or less correct. This was, here we are now. China is just passing the United States as the largest economy in the world and will keep rising according to this projection. The United States is the blue line, and India is the yellow line, which is projected to pass the United States in total GDP by the middle of this century. But more importantly for the potential of India, in my opinion, is the incredibly rich and long intellectual history of India, with its contributions over the centuries to mathematics and to culture in general, and in the last 2 centuries to science, with some wonderful institutions like the Indian Institute of Science in Bangalore and the Tata Institute in Mumbai, and some extremely accomplished examples of Nobel laureates such as Raman, Chandrasekhar, Bose, Homi Bhabha, whose last name disappeared, who founded the Tata Institute, and of course the brilliant mathematician Ramanujan. I have many Indian colleagues and friends. I know, and most of them graduates of IITs, I know what an incredible intellectual potential is represented in the over billion population of this subcontinent. And so I have been motivated for the last decade to work with my colleagues on trying to realize through this mechanism of theoretical institutes India's potential. And in particular on the International Center for Theoretical Sciences, which is a branch of TIFR in Bangalore, which we inaugurated just a few weeks ago in an opening ceremony. And I have the pleasure of introducing to you the director of that institute, my old friend and colleague, also a graduate of IIT Kanpur, Spenta Wadia. Spenta.
Thank you, David. So let me just take you straight to Bangalore. So the goal of the ICTS, I think you have got a very good idea of the institutions in the world which are conducting boundaryless research in various areas, is basically to bring together physicists, astronomers, cosmologists, mathematicians, and biologists from all over the world under one roof, and basically to really work together to solve the most challenging questions posed by nature. And our ambition is that some of these most challenging problems should be solved in India. I mean, why not? So here is a picture of the inauguration. And you can see over here, David Gross is actually sitting there with many other people. And you can see that some of the most distinguished scientists from all over the world attended for our inauguration. That was a couple of weeks ago. And you see, we would like to combine this type of coming together of scientists from all over the world with very outstanding in-house research. And this is very important. This is the second important mission of the ICTS, is to have highest quality faculty in various areas of theoretical sciences. And let me tell you, I'm very, very proud that today we have 13 outstanding young scientists actually working in our center. And it will grow to approximately 30 in the next decade.
Right.
So the third thing that we do actually, and this is very important, is to stimulate and harness the young minds of India. And I think in a country like India, as you would all appreciate, it is crucial to propagate the scientific temper, to make use of the scientists who are in this institute and its facilities to conduct very important outreach programs in science. I'd like to end just by a few photographs that I'd like to thank David for being participant in this extraordinary journey for the last 10 years in every respect, from the architecture plan to the construction to the advice. And here you see chief executive and some of us before the campus actually got started making. And this is more or less, it's a cartoon, but this is more or less what it looks like, minus the trees, of course. Those take time to grow. Thank you. Thank you very much.
Thank you, Dr. Gross, and thank you, Dr. Wadia. Wow. It's not every day we get to speak to a Nobel laureate. We have a number of trending questions. We don't have time for all of them, but I'll try a few. Dr. Gross, the number one trending question from this group is the ultimate. How big is the universe?
Well, it's getting bigger every day. So, you know, when we talk about the universe, we talk about the visible universe, that universe we can see. And as far as we know, extrapolating backwards, our understanding of the universe is that something called the Big Bang started it all off 13.7 billion years ago. And that means that we can't see any farther than 13.7 billion years times the speed of light. But the universe is expanding, so every year it gets to be a light year bigger from our point of view. Its expansion is accelerating. So at the moment, that was a great discovery, won the Nobel Prize 10 years ago. Where it will end is one of the deep questions we ask and try to understand. So the universe we can see is still growing. We can see farther and farther out because we have longer, takes longer for the light to get here. And the ultimate size we will be able to see is still unknown.
And this question, I don't think we have time for an answer, but it does tell you about this IIT crowd. They are very interested in signing up for a class with you. Why are inertial mass and gravitational mass the same?
Well, there is a, you know, that was discovered by Galileo, or Aristotle didn't understand it. Galileo discovered that. It's called the principle of equivalence. Newton used it, and Einstein took it as the foundation of his understanding, his theory of gravity, which we celebrate today, this year. 100 years ago, Einstein wrote down the final form of the theory of gravity, which was based on that principle of equivalence, that all bodies fall with the same speed because the gravitational mass that pulls them down and the inertial mass that slows them down are the same for all bodies. Today, we have ways of explaining that coincidence on the basis of deep principles of symmetry, which Einstein used to construct his theory if those masses were the same. So we think this is one of the most essential parts of the physical universe, that gravitational and inertial masses are identical.
Okay. Thank you. We would be here all day with a number of trending questions for Dr. Gross, but we do need to wrap this up. Thank you, Dr. Gross.
Pleasure.
Thank you, Wadia. Let's give him a big hand.